Okay, so here is reaction number 3, and I've got myself a ketone and an aldehyde, and it's reacting with sodium hydroxide and heat. So ketones and aldehydes can undergo reactions at an alpha carbon. An enolate is formed by removing a proton from the alpha carbon. We need an enolate for an aldol condensation reaction. Therefore, there must be an alpha carbon for an aldol condensation reaction to occur. So what is aldol condensation? It's when an enolate reacts with a carbonyl compound to form a beta-hydroxylaldehyde or beta-hydroxyketone, followed by dehydration to form a conjugated enone. You need 2 carbonyl compounds to play 2 roles: enolate nucleophile and electrophile. In my condensation, I'm given an aldehyde and a ketone. And hypothetically, if both compounds had an alpha carbon, 4 products could be formed, because the aldehyde could do self-condensation, with itself. Ketone could also do that. The aldehyde could attack the ketone, or the ketone could attack the aldehyde. However, the aldehyde does not have an alpha carbon because there are no protons there. As you can see here in the aldehyde, it's attached to this ring. There's no protons there on what would be the alpha carbon. So only the ketone has an alpha carbon. So we can only make 2 products: the ketone self-condensation and a cross-aldol condensation with the aldehyde. So sometimes, though, if this wasn't the situation like mine is, we would need to control the product if both the carbonyl compounds had an alpha carbon by adding one of the reactants slowly. That's in order to prevent that self-condensation reaction from occurring, because that's not the goal. We want to cross the products. So again, the aldehyde used here does not have that alpha carbon because it's attached to that ring with no protons. So the aldehyde cannot make an enolate because, as we know, an enolate is formed by removing that proton. So can't remove what's not there, right? So the aldehyde is basically naturally restricted to being the carbonyl acceptor. So the ketone then is restricted to being the enolate. So we can only form 2 products if the ketone reacted with itself again, and then if the ketone was the enolate and the aldehyde was the acceptor. So let's look at the ketone-ketone. Hold on. All right, there we go. So the ketone attacks the ketone. So this could happen on paper, but in reality, it can't happen because ketones don't like to find other ketones, because the ketone carbonyl is less electrophilic. So this, again, the product is hypothetically formed, but realistically very unlikely. So now let's look at the real mechanism here. So again, aldehyde's more electrophilic. It's restricted to being the carbonyl acceptor, and the ketone acts as the enolate naturally. So basically what happens first is a base. So we have our base, deprotonates the alpha carbon from this carbonyl compound, forming the enolate ion. So then the enolate will act as a nucleophile and attack the aldehyde. And then this will then form the alkoxide intermediate. But then we're gonna use water over here to protonate that intermediate. So then we get down here. And then what we're gonna do is we're gonna dehydrate it. So what allows the dehydration is the heat. So this reduces the OH group. So we're gonna see in our final product, we no longer have that OH group. So that's the simple mechanism for creating an unsaturated carbonyl compound with these favorable conditions, And again, we've got a nice conjugated system that stabilizes it. So this right here is the same as the one on the paper that's given. It's just kind of flipped 180. But yeah, that's our product, and that's all for today. Bye.